So hello everyone and welcome back. We have a couple of minutes before the start of class. Does anyone have any questions for me? So the question is, which chapters are covered for the midterm? Everything that we're doing up to and including today's lecture. So go through just the list of lectures online. Each one points to the chapters that were covered in that class or the sections of the book covered in that class. So you're responsible for all of that on the midterm. So if you want advice on preparing for the midterm, your best bet is to go to the course webpage, look at sample midterms from previous years, and try and do those. There's both a version of those where you can just look at the whole midterms, and there's a version that's linked to that was set up by some Carleton students where you can actually go online and take those midterms. So attempt them yourself, and you'll get a grade at the end. How similar are the sample midterm questions to the actual ones? Well, you can look at many of the sample midterms and compare, you can compare the sample midterm from fall 2014 to the sample midterm from fall 2015. That will give you an idea of how similar consecutive midterms are. So I think there's something like 10 or 11 old midterms available on the course webpage. So it's, I mean, for every, any question that we ask is probably similar to one of them on one of those midterms. Okay, so today and for the rest of the course, I want to start talking about probability. So this is basically the second half of this course, and it's a big chunk of this course. And in fact, we'll find that most of what we were doing even leading up to this, which was combinatorics, counting the size of sets, directly applies to problems that we want to solve in probability. It's likely that you've taken a course before that had some probability in it, most likely a stats course. So we're going to start from scratch here, and we're focusing on discrete probability. We'll only study discrete probability. So you can have taken such a course or not taken such a course, it doesn't matter. If you've taken such a course, my advice is to forget about everything that you learned there, because we'll do it all from scratch, from first principles. Okay, but before we get into the real technical stuff, I'll give you an example of a neat problem that you can solve using randomization, which means probability, that to understand the solution to, you don't have to really understand probability yet, other than to get maybe an idea that, for instance, if I toss a coin, then half of the time it comes up heads and half of the time it comes up tails. You have no way of predicting that. And if I toss a coin, if I turn around and toss a coin, and I remember whether it came up heads or tails, but I don't tell you, then you have no chance of guessing whether that coin was heads or tails that has any chance better than 50% of being correct. Okay. All right, so here's the story. Three friends, Michiel, Jit, and Pat, suddenly realize that they have been friends for 20 years, and they want to do something to celebrate this fact. So they get a very expensive bottle of whiskey and go on a camping trip. So they canoe out to an island, and their plan is to make a campfire and drink this whiskey together to celebrate their long-lasting friendship. So they arrive at the island early in the morning with their canoe. It's a little bit too early to start drinking whiskey right away, so they spend the day doing other things. Michiel, who is the most hardworking of the three, goes off to get some firewood. Jit goes for a hike. He likes to hike and explore. And Pat goes for a swim in the lake that they use to reach the island. So then evening comes, and they sit around the campfire. They say, okay, let's get that whiskey out now. So they go to their pack and pull out the whiskey bottle, but they find that it's completely empty. And it's not only just that it spilled or broke, but the seal is broken on the bottle. So someone broke the seal and drank all the whiskey. And since Halloween is coming up, we can make this a sort of spooky story. So the island that they're supposed to be on, that they're on, is supposed to be deserted. There should be no one else on the island with them. So this is disturbing to them for two reasons. One is there's a scary explanation for what happened, which is that there's some sinister person on the island, and if that sinister person is willing to drink their whiskey while they're off, who knows, maybe he's willing to come and kill them in their sleep while they're sleeping in their tents. So they don't want that. Another explanation is that one of the three just got greedy and decided to drink the whiskey when no one else was around. Okay, so either Michiel came back from his firewood collecting and drank the whiskey, or Jit came back from his hike and drank the whiskey, or Pat cut his swim short and drank the whiskey and didn't tell the others. Okay, so what they want to do now is have a way of distinguishing between those two things. Is there a sinister person who drank the whiskey, or did one of them drink it? On the other hand, the person who drank the whiskey doesn't want to confess because they've been friends for 20 years and doesn't want to risk ruining that friendship. So they're looking for some protocol, some rules that they can follow, that if one of them drank the whiskey, they'll know that happened, but they won't know who it was. And if none of them drank the whiskey, they'll also know that. And they'll know that there must be another person on the island. Okay? So this is called anonymous broadcasting. So one of these three people maybe has a bit, one that they want to broadcast. So if one of them is the drinker of the whiskey, they have a bit, one, that they want the other two people to know, and they don't want to identify themselves. So they're going to run a protocol to do this. And the protocol is going to make use of this XOR arithmetic, which is just arithmetic modulo 2, right? So in this arithmetic, 0 plus 0 equals 0, 0 plus 1 is 1, 1 plus 0 is 1, nothing very exciting, but 1 plus 1 is 0. Okay. So this is the arithmetic that they'll use. It's called XOR, or you can think of it as addition modulo 2. Okay, so let's call these people P1, P2, and P3. Their names are a bit too long to continually write. So here's what we do. Each PI picks a random bit BI. Okay? So each of them tosses a coin, and that gives them a 0 or a 1 that they keep to themselves. Okay? So this is a secret. Well, it's a partial secret. So now each PI whispers the value of BI to PI plus 1. Okay? So there's and this is modulo 3. Okay? So they're sitting around the campfire here. P1 has a bit B1. We'll draw that there. P2 has a bit B2, and P3 has a bit B3. That's what they do in the first step. So it's a 0 or 1. It's gotten by flipping a coin. And then each one whispers the value of their bit to their neighbor, their clockwise neighbor. So P1 tells B1 to P2. So that means that P2 now knows the value of B1, and so does P1, because P1 is the one who created it. P2 tells the value of B2 to P3, and P3 tells the value of B3 to P1. So this little picture here shows the three players, P1, P2, and P3, and the 3 bits, and the edges here mean that player I knows bit J. So P2 knows B2 and knows B1 also, but not B3. Okay? So now each PI computes a value Ti, which is just equal to Bi minus 1 mod 3 XOR Bi. Okay? So P2 here computes this value, which is B2 XOR B1. Okay? So they take these two things. This becomes T2, which is just the XOR of B1 and B2. P3 takes the XOR of B2 and B3. That becomes T3, and T1 takes the XOR of P1 takes the XOR of B3 and B1. That becomes T1. Now, now we compute a new bit. Computes, we'll call it Ti tilde, which is one of two things. It's either equal to Ti, or it's equal to Ti XOR 1, which means it's either equal to TI or you flip the bit TI. And when is it equal to TI? It's equal to TI if PI did not drink the whiskey. And otherwise, the person who drank the whiskey flips the bit. Okay. Did drink the whiskey. All right. Now, each player announces the value of that bit that they just computed. Okay. So now they compute they compute this value, and each one says out loud their bit that they've computed this way. It's either a 0 or a 1. They tell everybody. Okay. So now everybody knows T1, T2, and T3 tilde. And now anybody can compute the value now, right? So what do you get? You get each PI computes. Well, let's see what the formula gives us. We take T1 tilde XOR T2 tilde XOR T3 tilde. Well, what's T1? T1 is the XOR of B3 and B1. So that's B3 XOR B1. What's T2? Well, that's the XOR of B1 and B2. And what's T3? That's the XOR of B2 and B3. So that's the value of T1. So these things are T1, T2, and T3. But if one of them drank the whiskey, then one of them did this. So their thing that they put in is not just TI, but it's actually TI plus this this extra 1. Okay. So that means, so if none of them drank the whiskey, each one puts in TI. This is what you get. And well, if you look at, remember this modular, one thing you can see immediately from this modular arithmetic is if I take any bit and XOR it with itself, I get 0, right? 0 XOR 0 is 0, and 1 XOR 1 is 0. So any bit XORed with itself is 0, which means that you get cancellation here, right? B1 XORed with itself is 0, so those cancel. B2 XORed with itself is 0, those cancel out. B3 XORed with itself is 0, and those cancel out. So if nobody drank the whiskey, then the value 0 comes out from this formula. Okay? So that's if no one drank the whiskey. Otherwise, meaning one of them drank the whiskey, then this thing here the formula looks exactly the same, except one of them threw a 1 into it, so it's going to evaluate to 1. So this protocol then is correct. If no one drank the whiskey, a 0 comes out, and then they get really nervous because that means someone else drank the whiskey. If someone drank the whiskey, one of these three drank the whiskey, then a 1 comes out and they breathe a sigh of relief because there's not a killer, necessarily a killer on the island who's willing to drink their whiskey and kill them in their sleep, so they're happy about that, but they're still a little bit sad that they can't trust each other anymore, and maybe that's sort of the end of this very close friendship in any case. So it's a sad story in any case, but one is more worrisome than the other. And now, okay, so it does what it's supposed to do. It correctly, does Professor say today that not have class? So there's a question that no. There's a class today. I don't know what that means. If you're talking about my other class this afternoon, no, there's an exam this afternoon. Okay, so it does broadcasting correctly, but is it anonymous? So if I'm one of these players and the bit 1 comes out, can I figure out who did it? Well, let's convince ourselves that you can't. And why that is. So suppose I'm player 1. I didn't drink the whiskey, and but somebody did, so the bit 1 comes out from this thing. So as player 1, what do I know? As P1, what are the things that I know? Well, I know B1 and B3. I also know T1 tilde, T2 tilde, and T3 tilde because everybody knows those. So that's what I know, but not, what's the bit that I don't know? I don't know the bit B2. So I can try and figure out which, I mean, I can try and figure it out from these things, but I mean, let's see if I can tell. So I know one of these two guys, I didn't drink it, one of these two guys must have. Can I know which one? Well, what's this value T3 tilde? Because I know that one. Well, that's equal to B2 XOR B3, and possibly and this plus 1 if P3 is the whiskey drinker. I also see T2, which is equal to B1 XOR B2 XOR 1, but only if P2 is the whiskey drinker. Okay. So these two functions, these are mutually exclusive. Either P3 drank it or P2 drank it. So another way to write that is this one is plus x for some value x in 0, 1, and this one is 1 minus x for some x in 0, 1. And how do I, so what things do I know? I don't know the value of x. So x would be 1 if P3 was the drinker, x would be 0 if P2 is the drinker. But if I look at these things, I don't know x. I do know B3 because P3 told it to me. And I do know B1 because that's determined, that's my bit. I chose that bit. But I don't know B2. Okay. And which of these two formulas works depends on, I mean, in order to identify which of these two people it is, I need to know I need to know B2. So if B2 is 0, then I can figure out from the value of x which of these two it was, or from these two values which two it was, and if B2 is 1, I deduce the other thing. But I don't know B2, and so that means that my decision about which, if I try and identify which one of these was the drinker, the probability that I'm able to do that is no better than my probability of being able to guess the outcome of a coin toss without having seen the result. So it's not better than 50%, and well, if there's only two options and you can't guess with probability better than 50%, then that's really not, I mean, that's like you have no information at all. Okay. Does XOR, is XOR associative? Yes, it is. XOR is really nice. I mean, just think of it as addition modulo 2, if you like. Addition has all the nice properties. It's associative in particular, and so therefore XOR is. Yeah. So indeed, and that's what you do for P1. If that's not the one, if he's one of the non-drinkers, and the same symmetric arguments work for each of the two non-drinkers. Of course, the one who drank the whiskey knows who it was. So this thing is correct. It correctly tells you whether one of these three drank it, and it gives no information about who the whiskey drinker was. So in the literature, this is called anonymous broadcasting, and it generalizes to any number of players in which you have exactly one of the players who wants to send a message to everyone, but doesn't want to identify themselves. Okay? They don't want the person to know that the message came from them, and it works. I mean, it works similarly to this. So the n-player version is a generalization of this thing. And if you want to send more than one bit, then well, that's when you really think of this as XOR, and instead of these BIs being individual bits, they're whole bit strings, so random bit strings. Wow, so Dank Moose has a good question. If it was one of the three, couldn't you tell by how drunk they were if they drank a whole bottle of whiskey? Well, here's a thing about these three friends. They have a long history of drinking together, and they do that so often that a bottle of whiskey is not a problem. You couldn't tell whether they were drunk or not. In fact, probably even on the canoe trip over, each one of them drank a bottle of whiskey in the canoe before they even got there. So no chance of telling if one person is more drunk. So at the end of this protocol, so there's a question about this. At the end of this protocol, they've either figured out that none of the three drank the whiskey, if this sum is equal to 0, in which case they all grab their stuff, jump in the canoe, and race away before this person comes to kill them, or this bit is 1, and they realize that one of the three drank the whiskey, but somebody who is not, if anybody, so that means 2 of them didn't drink the whiskey, those 2 have no idea which one of the other 2 was the actual whiskey drinker. So that's the anonymous part. All right. So there's some motivation for the cool things you can do with randomized algorithms. now let's get on to the meat. And the nice thing about probability theory is that it's sometimes surprising, so you can get very surprising results, and sometimes even from the basic definitions, even though they seem tame and sort of obvious, surprising things happen. So most of the lectures from this point onwards, for the next little while, they will have us introducing some definitions or maybe some rules in probability theory, but mostly definitions. And then we'll see examples of those things and see that, okay, those definitions and examples, they behave like we expect, but then typically the class will finish where we look at an example, we guess what the answer should be, then we apply the rules and or the definitions we just learned, and the answer turns out to be completely surprising. Okay. So a lot of our classes are going to be like that. Today, that's probably not going to happen because the exciting part was this protocol at the beginning. Now we have to just get the basics under our belt before we can see the really exciting or really weird stuff. So the first thing is probability theory, like so many other branches of mathematics, introduces language for or names for things that we already have names of. So one of these names is something called a sample space. So a sample space, it's a set. Okay, so a sample space is a set. There's just a couple of conditions, and so the reason you call it a sample space is so you don't have to constantly say non-empty countable set. Okay? So it's a set that should be non-empty, meaning it has to have at least one element in it, and countable, meaning that informally you can list out the elements of the set like x1, x2, x3, x4, x5, and so on as the elements of the set. And if you follow that list, you will eventually see every element in the set. So it doesn't mean that it's finite. So that list could be infinitely long, but every element of the set appears in the list. Okay. More formally, countable just means that either the set is finite, so it just has a fixed number of elements, or there's a bijection between S and the natural numbers. Let's say the non-negative integers. So these are fairly natural things, these sets. All right, so the elements in S, those are called outcomes because we're thinking of, we imagine we're doing an experiment. All of the things that could happen in the experiment, all the results of the experiment, the possible outcomes are this set S, so each element in there is one particular outcome. And the subsets of S, those are called events. Okay? So sometimes there's a group of outcomes that you might group together into things that have some common property. You call that an event. So for example, if I pick a random number from 1 to 10, then the set S is just the random integer from 1 to 10. The set S is just the integers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Each of those integers is an outcome, and any subset is an event. So for example, I can think of the event, well, the integer that I picked is odd. So that's subset of 1 through 10. In fact, it's the subset 1, 3, 5, 7, 9. And so that's what's called an event. It's not an individual outcome, it's a group of outcomes that I'm interested in. Okay, so that's the sample space. And a probability function on a sample space S is just a function that takes elements from S gives them a real value between 0 and 1, called a probability. And it has this property that if I add up all of those probabilities in the set, I get 1. Okay? So intuitively, we think of this as you do some experiment, there's all these possible outcomes. Each one of those outcomes has a likelihood of happening, a number between 0 and 1. But if I run the experiment, then something happens. So one of the things in S has to happen. Which just means that all of those probabilities add up to 1. Okay. All right. So that's a probability function. And then a probability space is a sample space. Well, it's a pair. S and a probability function where S is a sample space and PR is a probability function on S. Okay. So a couple of things to note. Probabilities are between 0 and 1 always. So I'm not going to talk anymore unless it's very unless we're being very informal about percentages. Right, percentages are usually between 0 and 100. Just think of anytime someone gives you a percent, divide by 100. In fact, that's what the word percent means. It means out of 100. Okay. Yeah, so some of you are still thinking about the example. It takes some time to think about it, but don't skip the rest of the lecture thinking about it. Okay. So these are the definitions. Let's test these with a couple of examples. A really baby one is the following. We toss a coin. So imagine the experiment that we're going to do is tossing a coin. So if we toss a coin, there's two possible outcomes, a head or a tail. So in that case, we might say S is a set with two elements. One is H and the other is T, H for heads, T for tails. And so that's, that defines the sample space. And what about the probability function? Well, I think we believe that if we toss a coin, the likelihood of it coming up heads is the same as the likelihood of it coming up tails. So if we believe that, then we get that the probability of heads is equal to the probability of tails. And if that's true, then what we know is that, well, by definition, each of these things is a number between 0 and 1, but they both have to be equal in this case, if I'm assuming heads and tails are equally likely. And the second part of the definition of a probability function says that they have to add up to 1. So I need two numbers that are equal, so I need one number, and if I add it together, or if I multiply it by 2, I get 1. There's only one such number. It's a half. All right, so in terms of modeling, then if we're trying to model this coin tossing experiment using as a probability space, Well, the set of outcomes is pretty much indisputable. I mean, if we're tossing a coin, there's two outcomes. That's a pretty standard thing. And the only place that we're sort of making an assumption about the real world is if we assume that heads is as likely as tails. Physicists might tell us that that's not quite true, but for our purposes, it's a good assumption. Once we make this assumption, then this follows from the definition. Okay? So once you assume the two things are equal, then because they add up to 1, that means they both have to be a half. Okay, so that's an easy one. Here's another example. We'll toss 2 coins. And I don't mean that we take 2 identical coins in our hand and throw them up in the air and then look at what happens. I mean we take a coin, we toss it, we see that it comes up heads or tails, the first coin, and then we take, let's say, another coin or the same one, toss it, it comes up heads or tails, that's the second coin. So the order of the heads, the order in which we toss the coins matters, or at least that's what I'm interested in. So then in that case, you get a probability space that has 2 possibilities for the first coin toss and 2 possibilities for the second coin toss. So by the product rule, that means the size of that sample space is going to be 2 times 2 is 4, and it looks something like this. Heads, 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 tails, tails, heads, tails, tails. And again, it seems reasonable. Again, we're just modeling some real world thing as a mathematical object, a probability space. So we get to pick the model, but what seems to agree with what happens in the real world is that each of these 4 outcomes is equally likely. So that means that the probability of heads, heads equals the probability of heads, tails equals the probability of tails, heads equals the probability of tails, tails. And so now we have 4 numbers all equal, but if we add up those 4 numbers, they have to add up to 1, so they must all be equal to 1/4. Okay. Easy. Let's look at another example. We roll a 6-sided die. Okay. What am I talking about here? I'm talking about this thing. It's a cube. So it has 6 sides. On each of the sides, there are some dots. And what we care about are when we roll it, it lands on one of its faces or one of its sides, and opposite that there's a face. We look down on it, we count the number of dots, that's what we care about. Right? That's the standard way we use 6-sided die. We treat it as if we rolled a number. So then the sample space, so the things that can happen when we roll a 6-sided die are we can get any of the numbers 1, 2, 3, 4, 5, or 6. And we really rely on the fact that that each of the, I mean, if you think of, we have this intuition that all those outcomes are equally likely. And so by the same argument we've been using, that means that the probability of any particular outcome is 1/6. So for any I in 1 to 6, the probability that we roll an I is just 1 over 6. All right. Another example. So one thing you may be noticing here is so far, okay, the sample spaces, they're kind of easy to define. The probability functions have been sort of special so far. We get, you know, they're what are called uniform probability spaces, where each of the outcomes is equally likely. Maybe there's examples of probability spaces where that's not the case. So let's try and build up one of those. Let's try a different one, which will also be uniform, but from it we can build more complicated things. So we roll 2 6-sided. Guess I should be consistent here. And now I should be really, clear about what I mean. 1 red and maybe 1 blue. Because it is very common when you're rolling 2 dice to just take 2 dice in your hand and throw them and not identify which one as being the first die and then the other one as being the second die. I want my outcomes of my rolls to be ordered pairs where there are 2 numbers between 1 and 6 where the first one is what came up on the red die and the second one is what came up on the blue die. So they're not identical dice. Or it's 1 die that I roll twice and remember which was the first outcome and which was the second outcome. All right, so then S, well, what does S look like then? Well, it's 2 of these things. So it's what you call the Cartesian product of S and S, or you call it S squared, but let's be explicit. It's actually all the pairs ij where I is a number between 1 and 6, an integer from 1 to 6, and j is an integer from 1 to 6. Okay. And again, there's no reason to believe that any one of these outcomes, so how many outcomes are there here? Well, there's 6 choices for I, and there's 6 choices for j. So, yeah, I should be, let's call that one S with an underline, just to distinguish between those 2 things. So there's 6 choices for I, 6 choices for j. So that means that the size of S is 36, 6 times 6. And no reason to think any outcome is more likely than any other outcome. So that means that the probability of a particular outcome ij is 1 over 36. And that's for each ij in 1 to 6. Okay. So for each choice of I from 1 to 6 and each choice of j from 1 to 6. All right. So those are just some examples of different probability spaces for fairly common things that happen fairly commonly in regular life, or at least if you're playing games. Now, let's focus on this one because it's the first one we can ask sort of interesting questions about. So I roll 2 6-sided dice, and some pair of numbers comes up. So we're going to focus on this one. We'll forget about these ones up here. So let's, for any integer k from 2 up to 12, let's define the event ak, and we frequently, when we work with probability, we remember that events, of course, are just subsets of the sample space, but we will often just define them in plain language, because, you know, in plain language that also, you can define things that way. But we should always keep in mind that they're subsets of the probability space. So the event, and we usually put quotes around them when we define them this way. The event AK would be the sum of the two dice is equal to k. Okay. So for example, if I look at, if I take k equals 4, then I'm interested in all of the ways I can roll two dice and get a 4, and they're not too hard to list, right? So the first thing could be a 1, and the other one could be a 3. Those add to 4. Or maybe the first one is a 2, and the other one is also a 2. Or maybe the first one is a 3, and the other one is a 1. And now there's no more options, right? Because if the first thing I roll is a 4, then it doesn't matter what happens after that, I'm going to get something bigger than 4. So that's the event A4. The sum of the two dice is equal to 4. So what's the probability of this? So, you know, I'm playing Monopoly, and I need to land on a property which is 4 squares away, or I would really like that. So I'd like to know, well, what are the chances that my next roll is going to take me right to that space that's 4 squares away? For that, I need to compute the probability of this event, A4. So the probability of A4, so for that, I want to add up all the probabilities of the individual events, or the individual outcomes that make up A4. So that's going to be the probability of 1, 3 plus the probability of 2, 2 plus the probability of 3, 1. Okay, and that is 1 over 36 plus 1 over 36 plus 1 over 36 is 3 over 36, which is 1 out of 12. So my chances of rolling a 4 are not particularly high. I only have a 1 in 12 chance of rolling a pair of dice whose sum is 4. And why do I say that that's not particularly high? Well, for instance, there are only 11 possible outcomes when I roll two dice and take their sum, and so this one is not even, it's not even 1 out of 11, right? It's less than 1 out of 11. Okay. what about different values of A here? So what about, you know, A1, A2, A3, A4, and so on all the way up to A12. There's no A1, so we start at 2. Well, for that, we can draw a table. We have the first die that we roll, let's call it D1. It can take on any of the values 1, 2, 3, 4, 5, or 6. We have the second one, D2, which can also take on any of the values 1, 2, 3, 4, 5, or 6. And the way you read this table is you're going to write a value here which is just the sum of those two dice. So 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 8, 4, 5, 6, 7, 8, 9. So you can think of this as actually this is an exhaustive listing or of a way of listing out this set of 36 possible outcomes. 6 for the first one, 6 for the second one. That gives us 36 places. And on each of those places, I'll just write the sum of those two because to figure out these AKs, that's what I need. So what's the probability that I roll a 2? Well, out of the 36 possible outcomes here, there's only one of them that gives me a 2, and that's snake eyes. If I roll 2 ones, I'll get 2. Otherwise, I'll get something other than 2. So that's 1 out of 36. What's the probability that I roll a 3? Well, if I look at this table, I can get that by rolling a 2, 1 or a 1, 2. So that's going to be 2 out of 36. Probability that I roll a 4. We calculated it already, but here it is in the picture. It's these 3 outcomes here. 1, 2, 2, 2, or sorry, 1, 3, 2, 2, or 3, 1. Probability that I roll a 5 is 4 out of 36. Probability that I roll a 6 is 5 out of 36. Probability that I roll 7, 6 out of 36. Right, there's 1, 2, 3, 4, 5, 6 of these things give me a 7. So it keeps going up. It's more and more likely that I'm rolling higher numbers, but it peaks here at A7, at rolling a 7. After that it decreases, because if I look at the probability that I roll an 8, that happens. I can get a 6, 2, I can get a 5, 3, I can get a 4, 4, a 3, 5, or a 2, 6. There's only 5 of those. And it goes down, down, down. Until finally the probability that I roll a 12, well, you see that that looks a lot like a 1. The only way that I can roll a 12 is if I roll 2 6s. All right, so if you play games of chance, dice games, in particular craps, you had better understand this this distribution here. Okay? So it's really important that 7 is the most likely outcome when you roll 2 dice. Okay. All right. So let's keep that in mind. So now I said that there are a couple of, so those are the definitions I wanted to introduce. I want to introduce a rule as well. But first, so remembering this definition of AK, this thing here. First, one question you might ask is, well, if probabilities, so events are sets, and the probability of an event is the sum of the individual probabilities of the outcomes in that event, so the elements of that set, then what's the probability of the empty set, right? So this is the empty event. So, well, you just apply the sort of definition. You add up over all the elements in the empty set, the probability of that element, but there are no elements in the empty set. So this is an empty sum, and you may or may not have ever thought about what an empty sum means, or how it should be defined, but the only definition that makes sense is to say that an empty sum has value 0. So the probability of the empty event is 0, and a sort of helpful way to think about that is if I run the experiment, because all the probabilities add to 1, something has to happen. Right? Some element has to come out as an outcome of this experiment. And so the probability that nothing happens is 0. But more important is the following. So if A and B are disjoint, so these are, we have a sample space S, and we have 2 events, A and B, subsets of S, and if they're disjoint, so remember that's when we're talking about these things are just sets, so disjoint means they have no elements in common, just like in this picture. Well, then what? The probability of A union B, all right, so A union B is a set, so we know how to do that. We take the sum over X in A union B of the probability of, well, let's be consistent, we call individual outcomes, omega is a good name for them. So the sum over omega in A union B of the probability of omega. But what does that mean? Well, that means we go through A and we add up all the probabilities of the individual things, and we go through B and we add up all the probabilities of the individual things. And since A and B are disjoint, well, we could go through all of A first and add up the probabilities. And then we can go through all of B and add up the probabilities. And since they're disjoint, we're never going to count anything twice this way, which, well, what's this sum here? This is just the probability of A. What's this second sum here? This is we go through B and add up everything. This is just the probability of B. So if A and B are disjoint, then the probability of A union B is just equal to the probability of A plus the probability of B. Now, if you've been paying attention, that formula should look familiar. Let's just get rid of the intermediate calculation. And say, looks like that. So think about it for a few seconds if you've seen a statement like that or a rule like that before. And I'll tell you what it is in 30 seconds or so. Or what you've seen before that looks exactly like this. But yeah, so that's this thing here. Very useful fact. If A and B are disjoint, you have an easy way to compute the probability of their union. So, and more generally, if A1 up to AN are pairwise disjoint, then the probability of A1 union A2 union and so on union AN is just equal to the sum of their individual probabilities. And the picture there is just this. There's the set of all outcomes. Here are these individual disjoint events. A1, A2, A3, A4, up to AN. If I want to know what's the probability of their union, so the big event that includes all of them, you just add up their individual probabilities. And it only works because they're disjoint. Otherwise, if they're not disjoint, you would be counting some things twice. You'd be adding some probabilities twice. Okay, so by now, hopefully you've recognized this thing. This, we'll give it the same name. It's the sum rule for probabilities. So, right, when we wanted to know the size of A and B, we said if A and B are disjoint, then the size of A and B is the size of A plus the size of B. And similar rule with exactly the same justification applies for probabilities of the union of disjoint things. If I sum up over all the things in A and then sum up over all the things in B, I'll count everything in A union B and I won't count anything twice. Okay, and same thing here. Unfortunately, just like the sum rule, it suffers from requiring that A and B are disjoint, and we'll see that when A and B are not disjoint, we'll have to do the same thing. We'll have to use a principle of inclusion-exclusion, but for probability, not for the sizes of sets. But for now, let's see how we can use the sum rule. And we'll do one example in two ways. We'll take away these definitions here. So we're still working with this experiment where we roll 2 dice and we take their sum, which really you can think of, well, either as the underlying probability space has 36 outcomes, each of them is equally likely, but then they define the sum, or there's a second probability space where the outcomes are the integers 2 through 12, and this is the probabilities of each of those things. This is a non-uniform probability space. They don't all have the same probability of happening, but let's stick with this one for now. So what is the probability that the sum of 2 dice is even? Okay, so think about this for a second. So you will have, if you think about it, if you just don't think at all and make a wild guess, you're probably going to guess that the probability that the sum is even and the probability that it's odd should be the same thing. And since the sum is either even or odd, that should mean that it's a half, so it's equally likely to be even or odd. But then if you think a bit longer, you might be concerned by, well, why should it be a half? Right? Like, look here, the most likely the most likely outcome is an odd number. So that already suggests that maybe it's not as obvious as, so the most likely individual outcome out of 2 through 12 is an odd number. So maybe it's not a half. But we can work it out. So let's do that. When is the sum of 2 dice even? Well, it's even if it's 2, or it's 4, or it's 6, or it's 8, or it's 10, or it's 12. Those numbers, we have them all here. We've computed them already. So it's not a problem we can't solve. So let's do that. So it's 1 out of 36 plus 3 out of 36. Well, we're going to use the sum rule. Let me go slowly here. That means that it's equal to the probability of A2 plus the probability of A4 plus the probability of A6, and so on up to the probability of A12. Why are we allowed to use the sum rule? Well, let's just look at those sets. We can draw them here and see that what's A2? Here's the set A2. What's A4? Well, there's the set A4. What's A6? There's the set A6. Here's A8, A10, and A12. So indeed, these things are disjoint, right? That looks like this picture here. Imagine this is the whole set of outcomes. There's the 36 possible outcomes. There's a set A2, A4, whatever. They're all disjoint. None of them are overlapping. So we get to use the sum rule to compute this thing. And when we do that, it's a bit tedious. We do 1 out of 36. We do 3 out of 36. We get a 5 out of 36. We get another 5 out of 36 for A8. We get a 3 out of 36 for A10, and we get a 1 out of 36 for A12. And what do we have? I see 9 for these, 9 for these. 9 plus 9 is 18. That's 18 out of 36, which remarkably is a half. But actually, looking at it now, it was even less obvious that this was going to work out to a half. Right? Because if I do the same thing, what's the probability that the sum is odd? Well, then I have to add up these numbers. I get a completely different looking sum that happens to work out to a half. Okay? I would get a sum that has a 2 out of 36, a 4 out of 36, a 6 out of 36. I mean, it has less terms even. And so, it's a little, I won't say surprising, but it wasn't obvious from the outset that the answer would be a half. Okay. So, all right, so that's one thing, one way to do it. It was a little tedious. We had to add all these things up. So if this was a bigger problem, like, I don't know, more dice, or maybe there were 20-sided dice, sort of Dungeons and Dragons dice, then it would take a while to do it this way. So let's see if we can find a shorter way, or at least a way that if we used it for 20-sided dice would somehow lead to less calculating. And here's how another way to answer this question. So remember, our dice are called I and J. The outcomes that come up are called I and J. So I plus J is even if, and only if, I is even, or let's say I and J are both even, or I and J are both odd. That's true, right? If I take two numbers and add them together and they're even, well, that's because both numbers were even or both numbers were odd. If one was even and one was odd, I would get an odd number. In fact, that's basically what we saw with the XOR operation, which is arithmetic modulo 2, the first thing we looked at in this class. So that's a sort of basic thing. So then let's define two events, A and B. Let's define A to be I and J are both even, and let's define B to be I and J are both odd. Okay. So then, probability that I plus J is even, well, that's equal to the probability of A union B, right? If I plus J is even, that's because I and J are both even, or I and J are both odd. Well, these are definitely disjoint sets, right? If they're both even, then they're not both odd, so that's definitely disjoint. So we can use the sum rule. And we have seen now that, well, what's the probability of any set in this thing? Well, each individual item has probability 1 out of 36. So to figure out the probability of the whole set, we just need to know the size of the set and divide it by 36. So that's just equal to the size of A divided by 36 plus the size of B divided by 36. Well, how do we figure out the size of A? Well, wait a minute. This is just a counting problem, right? I have, I'm asking how big is the set A that contains the pairs I, J, where I and J are both even and they're between, they're in the range 1 through 6. So A is just equal to the set ij, where I and j are either 2, 4, or 6. Okay. So I have 3 choices for I, and I have 3 choices for j, so that means that the size of A is just 3 times 3 is 9. And the same thing works for B. B is just the pairs ij, where each of I and j is taken from the set 1, 3, or 5. And the size of that, 3 choices for I, 3 choices for j. Which means that this is 9 out of 36. It's 18 out of 36 is a half. So there's a second way of doing this, which, well, super quickly goes back to something we're familiar with. So basically reduced it to the problem of figuring out the size of sets A and B, and those sets A and B had really simple definitions that we could immediately figure out their size using the product rule. Okay. So this is sort of the first example where everything we've been doing to study sizes of sets will immediately allow us to solve probability questions. In particular, in these uniform probability spaces, where every outcome is equally likely, then knowing the probability of an event is the same thing as knowing the size of that event. And you just have to divide by the number of outcomes. And I think you could see now how we could push this through to something like a 20-sided pair of 20-sided D&D dice, without having to make a table with 400 entries in it, which is what we would have to do here. Okay. So exercise for you at home, figure out the probability that I plus j is even if I is the outcome of rolling a 20-sided D&D die and j is the outcome of rolling a 20-sided D&D die. Figure out what the probability is that their sum is even. Okay. So that's a good place to stop today. I'll take any questions that people have. Yeah. So there's about 30 seconds of latency or more, so I'll wait a minute. So a question is, how do you deal with 20 dice? 20 dice is more of a problem because you don't have this nice statement. In fact, even for 3 dice, things start to get messy because you have to ask the question, when is I plus j plus k even? Well, I plus j plus k is even when I, j, and k are all even, or maybe I is odd, but j and k are even. maybe j is odd, but I and k are even, and so on. Then there's a bunch of cases, so you get more of these things. You don't just get two. You don't just get sets A and B, those you've got to work out. And now if you're trying to go up to 20 dice, well, you're basically, you have to look at all the ways of choosing. It's basically an even number of indices in those dice, essentially. So the even number being the ones which come up as even. Right. You can think of the set A as both dice came up even. The set B is none of the dice came up even. So there's a relationship between subsets of even size and the sum being even. How does independence affect these probabilities? Well, we haven't defined independence yet, so this is the part where I want you to forget anything that you have learned so far. So we haven't defined independence. If you are thinking back, well, we defined our way out of independence here because we just said, this is the way I'm defining my probability space, that the probability of any particular outcome, ij, is 1 over 36. If you were thinking of defining this in terms of mixing two probability spaces, the first one and the second one, then ultimately the reason that we get 1 over 36 here is because the rolling in the first space, so rolling the first die, is independent of the outcome on the first one is independent of the outcome on the second one. But we defined our way out of it here. We didn't say anything about independence. It's just, this is the definition of our probability space. Can you use recursion to deal with more dice? I'm sure that there's some way to argue it using induction, but I haven't worked that out. So all that to say, dice with more sides, they're not difficult, but more dice makes this problem harder. And you can imagine dice with an odd number of sides and see what results you get there. What if you have you live in some universe where you can have 9-sided dice where all the outcomes are equally likely? What's the probability that you get an even number or an odd number when you roll 2 of those and add them up? All right, so thanks for showing up today, and I will see you next week already. We missed our Monday class. We'll be doing a review. You can look ahead at the schedule. We'll be doing a review on Monday, and then the exam on Wednesday.